what I'm going to be doing here, and that was George Benson in the background, is trying to demonstrate the use of an analog discovery 2 in testing HiFi amplifiers. Now, I've recently done a small series on how tube amplifiers work, including how tubes work and tube circuits, and a two-part explanation of the Williamson and the ultralinear and so on. This is not going to be a measurement on tube amps. For one thing, I don't have a really good tube amp to use. If you watched my restoration of the SX62A Hallicrafters, you'll know that it has a fairly high fidelity monophonic amplifier in it, but I certainly wouldn't call it HiFi. And while I have some other amplifiers that are tube amplifiers that are in about that class, none that are really high fidelity. So what I am going to be doing is showing the use of the analog discovery on this amplifier, which it is a Panasonic, and I'll show you a little more about it in a minute. And up over here you will see some of the equipment that I would normally use for testing an amplifier. This is a Sencore power amplifier tester at the top, right here. And below it is a Sencore FM stereo analyzer. It can also do AM stereo. That never really caught on too well, but these are more professional instruments intended for actual service depots where accuracy and the speed of repair and so on are important. I'm going to be using these to verify the operation of the analog discovery. But the basic work is going to be done using this analog discovery 2. Now, if you have an analog discovery 1, I think you can do the same thing. And I have an analog discovery 1, but I'm not going to be demonstrating that. I have used it in some previous videos, and I refer you to those. What we're going to be doing is using the analog discovery to do these kinds of tests. The first test is a power output test, and we're going to do that under simulated worst case conditions. That is, we're going to be driving, we're only going to be testing the stereo amplifier. That is what is normally called the front of a surround sound amplifier. Now, this amplifier has a subwoofer and also surround sound speakers or rear speakers, whatever, but I'm only going to be testing the stereo amplifier part. We'll test it with all channels. However, I'm only going to be testing it driving the two front channels. And normally you would do this at low line voltage, and while I have adjustable transformers to be able to do that, for this, since I'm primarily showing how to use the analog discovery, I'm not going to be running the amplifier at low line voltage. I am going to be using a dummy load. And in case that you don't have a dummy load, what you can do is use a power resistor or a set of power resistors, preferably mounted to a heatsink. The unit that I'm going to be using, which is this Sencore unit, has a pair of 250 watt dummy loads built in, and I'm going to be using that not because I couldn't use a homemade dummy load, but because that also gives me the ability to do a bunch of tests on the output, like wattage and RMS voltage and so on, and that is primarily to double check the analog discovery and see how accurate its readings are. So you do need a dummy load for the power output. Then we're going to be doing a frequency response check, and that normally is done using a sine wave. That is a single steady state frequency. When I say steady state, you of course change the frequency, but at any given time you're only operating on one frequency. So the sine wave might be sweeping, say, from 100 hertz all the way up to 100 kilohertz, but at any given instant it's one sine wave. And for that, we're going to be using the network analyzer on the analog discovery. The second kind of response, in addition to steady state, is what's called transient response. And this is quite important. A lot of people fail to perform this test. You should do a square wave analysis of any amplifier, because without subjecting it to transients, you aren't going to find things like hidden oscillations that are inaudible in the output. You'll hear them in the music, but they are very hard to pin down. It's much easier to use a controllable source like a square wave. And finally, we're going to be looking at distortion. Now, this particular amplifier does not have an intermodulation distortion specification. We're going to be doing primarily harmonic distortion, and for that we're going to be using the spectrum analyzer. If you don't have an FFT, you can do most of this work with an oscilloscope if it has a fast Fourier transform. Now, the one thing that's hard to do with just an oscilloscope is the swept frequency response that we're going to use the network analyzer for. However, if you have a sweep generator, an audio sweep generator, and an oscilloscope, you can also do that. And for that, if you want to see how that's done, you watch my video on sweep generators. Okay, here is the amplifier, and the CD is paused. I'm going to start that, and then I'm going to move the selector to the auxiliary input. The waveform generator number 1 is connected back to scope number 1 input. It also is teed, and this is feeding the auxiliary input of the amplifier. The second scope channel is connected to the output of the amplifier, and that is done over here with this cable that is paralleled on the dummy load in this unit. Here is the waveforms software on a Windows 10 computer. It opens it up and then looks for the analog discovery. After it finds the analog discovery, you can then open a scope and a wavegen. And now what we're going to do is we're first going to simply put a 1 kilohertz sine wave through the amplifier. I've moved the scope window up to this larger display, and you hear the 1 kilohertz. I'm now going to turn the volume down on the analyzer so that I don't have to compete with that extremely interesting 1 kilohertz. What you see in yellow is channel 1. That is the input. That is currently set to 500 millivolts per division. So as you see, we're generating about 200 millivolts. The blue is connected to the output across an 8 ohm dummy load, and it is set to 500 millivolts per division as well. And right now, the Sencore generator says that we are generating about 4 and a little bit over 4 watts RMS. I'm going to add a defined measurement to channel 2. It's a vertical measurement, and it's going to be AC RMS. And now you see the AC RMS shows it's about 5 volts RMS. I'm going to turn this down until the Sencore reads 5 volts. And now the Analog Discovery 2 is reading 4.12. Now I will point out that the Sencore is reading the voltage right across the dummy load, whereas the Analog Discovery, there is a considerable cable length. Yeah, and it does look like there is a difference between the two. So I'm going to have to look at that a little bit, but in the meantime, let's move on and do the measurement for the total output. What I'm going to do is turn the amplifier up all the way. That's with 0 dB showing on the front panel. And you notice that it says there's about 5 volts on the Analog Discovery. So we'll compute the power there. The Sencore says that it is putting out 7 watts RMS. So now to keep from heating up the amplifier, I'm going to turn the signal down. And now we'll move on and do the next of our tests. Now you see the network analyzer set up, and if you have questions about this, I have done a video on the Analog Discovery network analyzer. That one was actually done with the Analog Discovery 1. This is the Analog Discovery 2, but they're essentially the same. So as you can see, the frequency response of the amplifier meets the specifications. That is, this is 100 hertz on the left. This is 20 kilohertz here. It goes all the way out to 100 kilohertz logarithmically, but you see it falls off rather dramatically beyond about 20. So as to an amplifier, it fits the specification. You'll notice down here, this is a rather interesting phase diagram. This shows the phase shift through the amplifier. Now, phase shift is relatively undetectable by the human ear and brain. You can only detect it with equipment like this, and for that reason, most amplifier designers don't pay a lot of attention to the phase shift. However, it does make a difference, particularly when you are playing complex waveforms. And in a minute, when we look at a square wave, I'll talk about this a little bit more. Here you see the Analog Discovery scope. The yellow is channel 1. That is the input to the amplifier. The blue is channel 2. And what I've done is I've gone to a 1 kilohertz square wave for the input. This is not unusual. This shows you there's a phase delay through the amplifier. Then the amplifier begins to react. It overshoots and then comes back at about the time the next cycle begins, which then drives it negative. And you may notice that there is a phase 180-degree phase reversal plus some additional phase delay, in that it's when the input signal is going negative that the output signal is going positive. So there's a basic 180-degree phase reversal through this amplifier, the way I have it connected. Now, if you reverse the output, you'll get exactly the opposite of this. So don't pay much attention to the 180 degrees. While you might want the output to look exactly like the input, in an audio amplifier that's not really necessary. What you do want to watch for, though, is whether at any of these points, when the amplifier is transitioning and when it is basically falling back to its steady state level, do you get any oscillation? And to see that, what we're going to do is look at it expanded a bit. Now, you may notice that the input has some overshoot in it by itself, but the main thing we're interested in is, does the amplifier transition smoothly from one state to the other? And this is a pretty rapid transition for an audio amplifier. And then, does it hold its value? In other words, during this long time that the input is at a DC value, does it hold its value? And this amplifier is frankly average. And I should point out that these are the kinds of tests that I normally perform on an amplifier. They're not necessarily all the tests you would perform, but especially if you thought you had some other problems. You'd also do a listening test. There are some CDs you can buy that can test a number of things. I have a DVD that will test a surround sound system and things like that. But this is sort of the basic stereo amplifier testing procedure. Now what we're going to do, just for purposes of illustration, is put a triangle wave in. Now you see there, the input is a very accurate triangle wave, showing that the Analog Discovery's waveform generator is pretty linear. You'll notice that the amplifier, on the other hand, does not produce a linear rise. It's more like an RC or resistor capacitor time constant. And once again, that's not unusual, particularly with RC coupled amplifiers. Okay, I think that's probably enough for square wave analysis. Now let's take a look at the distortion. On the screen now is the spectrum analyzer of the Analog Discovery 2. And what it is showing is the harmonics, or the harmonic distortion. I'm feeding a 1 kilohertz 200 millivolt sine wave into the amplifier. The spectrum analyzer is looking at the output of the amplifier, and you see down here is 0.1 kilohertz or 100 hertz, and that's the far left. 1 kilohertz is this high peak here, which shows about 0 dB. Then there is a spike here, which is about 2 kilohertz. That's the second harmonic. There are also some little spikes in here, but they're hard to read. And with the averaging that I'm using, which is linear dB average and only a count of 50, you're not going to pick out very many of the small ones. The ones that are really of interest are the spike at about 48 kilohertz, and that I don't think is actually coming through the amplifier. I think that is feed through from the FM pilot generator. But nonetheless, there is about a 48 kilohertz signal, and then out here around 96 kilohertz, which is twice the 48. I think these two are actually artifacts, and since they're outside the listening spectrum, there's little, if any, interest in those. What we are interested in is going down to, for example, 20 kilohertz and looking, and you notice it takes a second for it to do all the counting, the averaging. And since I have reduced the span, it's a little harder. Now you see, we start to see a spike at around 8 kilohertz. There, once again, this is 3 kilohertz, which is the third harmonic. This is 1 kilohertz. So this is the third harmonic. And then you see a harmonic around 8 and another one up around 15 kilohertz. But that is minus 50 dBV, that is dB volts down from the output. So this is the most significant, normally the most significant harmonic if you have a lot of harmonic distortion. And it's about 60 dBV down. The 8 kilohertz is down about 50 dB, and the 15 kilohertz is down about 55 dBV. So this gives you an idea of how you can look for distortion, and we could calculate these out and calculate the total harmonic distortion by adding up all of the harmonics. But from just looking at the output and general experience with amplifiers, this is about what you're normally going to get. This is less than 1% total harmonic distortion with a 200 millivolt input. Now this is not intended to show you all the features of the Analog Discovery 2, nor all the ways amplifiers could be tested. This is simply a way that I test amplifiers, and we have discovered that there is an anomaly between the RMS voltage computed by the Analog Discovery 2 and the Sencore RMS voltage. I'm going to be investigating that because it's possible that the Sencore calibration is now off. It has been a couple of years since that power amplifier analyzer was calibrated, and it could be that it's reading a little high. You remember it was reading about 7 volts RMS when the Analog Discovery was reading about 5. So, as I say, I hope you have learned something from this, and if anything, I hope it encourages you to get an Analog Discovery and use it. It can be used for a wide variety of things, not just amplifier testing, but for all kinds of electronic test and measurement. So, look forward to some more along these same lines, but in the meantime, have a good day.